What's going on, everyone? For those of you who don't know me, my name is Jonathan Riddell, and in this video I'll be giving a talk entitled Concentration of Quantum Equilibration and an Estimate of the Recurrence Time. So this is a little peek into my overall research direction and a recent result. So this work was done in collaboration with Nathan Pagliaroli and Alvaro Alhambra. Nathan is at Western University and Alvaro is at the Max Planck Institute for Quantum Optics. This work was completed at the end of my PhD, where I was working at McMaster University and the Perimeter Institute, and now I am at the University of Nottingham. So the overall theme of my research is a very intuitive and for me a very exciting question, and that is, how does statistical mechanics emerge from unitary dynamics? Or to put it another way, how does statistical mechanics emerge from quantum dynamics? So typically when you take an undergraduate class in statistical mechanics, if you were to approach this problem dynamically, you would usually cite ergodicity. Ergodicity tells you that the time averages that you might do would be equal to phase space averages, or the averages you would carry out with the ensembles of statistical mechanics. Now, if you wanted to avoid the dynamical question altogether, you might introduce some equal a priori probabilities for energetically accessible microstates. Now, in this talk, what we're going to do is we're going to focus on isolated quantum systems with, usually we have in mind, finite range interactions of the following form. So our Hamiltonian H is a Hamiltonian that is built off of locally interacting terms that I've called H subscript x here. And throughout the talk, I am just going to be labeling the energy eigenvalues and the energy eigenkets in the following way. So just to dial things in more, to give you some intuition, we're going to be thinking usually about lattice type systems. So they don't have to be on a square lattice, but what we're usually looking at is some type of lattice type structure with degrees of freedom on that lattice. So we might be interested in, for example, fermions interacting and hopping on a lattice, or we might be interested in spins on a lattice interacting in some capacity. So typical models for things like this would be the Hubbard model, or spin type models like the Heisenberg model. In fact, throughout this talk, I'll show you some numerics. All of these numerics are going to come from a Heisenberg type model. Now, the actual content of that model doesn't actually matter. The thing that matters is that I have carefully selected the model for which the numerical examples will be shown such that it exhibits the type of dynamics that we're interested in this talk, and that is thermalizing dynamics. Now, if we were to sketch the story of the emergence of statistical mechanics from some dynamics, we might do something like the following. So suppose this black arrow is the arrow of time. So at t is equal to 0, we might find our system far from equilibrium. Then if we waited a certain amount of time for the thermalization time, our system would reach static equilibrium, and it wouldn't just reach any equilibrium, it would reach an equilibrium that is described by the ensembles of statistical mechanics. Now, after this point, we expect the system to stay in equilibrium. And this is true for systems, and this is true for most times, but for finite systems, we know that this is only true up to rare recurrences. And these rare recurrences come to us from the Poincare recurrence theorem, which I will talk about later. So if we were to now cast this story in the language of quantum dynamics, we would get the following. So suppose we initialize our system in some pure state psi, we can then expand it in the energy eigenbasis and time evolve it in the usual way. Now, what you'll notice here is that this vector, or sorry, this state, the pure state, is just a vector. So its components or its entries will just oscillate around in the complex plane forever. So it will never, the state itself will never go to equilibrium. So instead of just tracking the state, we also introduce usually a local observable A, and we track its evolution in time. Now, when I say local, what I mean is it has support somewhere on some subsystem of the lattice. And why do we pick a local one usually? We pick a local one usually because we can then define a complete basis of observables on some subsystem, and this will characterize the subsystem state. So then what we expect to happen is that if we wait long enough, our system or our observable will relax to some equilibrium expectation value that I wrote as A of infinity here. And of course, this is an abusive notation. Our function is an almost periodic function. And so what that means is that this limit, strictly speaking, doesn't exist. So instead, what we will define the equilibrium value in the following way. We will introduce omega, which is the diagonal ensemble. And the diagonal ensemble is just the infinite time average of our state. And then if we do expect to find an equilibrium emerging from our dynamics, then the equilibrium expectation values will be given to us by the expectation values of our observables with respect to omega, the diagonal ensemble. So just for some intuition, here is some dynamics of an example observable model and state. Now what you'll see is on the y-axis we have our observable A, and on the x-axis we have time. In the legend, I have put this variable d, and d is the distance to equilibrium for our observable's expectation value in time. And what you'll see here is that even for a modest system size, so this is only 18 spins on a lattice, that even for this modest system size, our observable does relax to within a certain precision or error to equilibrium for a modest amount of time. So equilibration does occur. Some notion of static equilibrium seems to exist here. So we don't expect, as I said previously, for this equilibrium to just be any equilibrium. We expect it to be the equilibrium where our observables' expectation values will eventually be, well described by the ensembles of statistical mechanics or, thermal averages. So as I've written here, we have the Gibbs state or the canonical ensemble, which is characterized by this inverse temperature beta. Now, how do we actually get there? Just looking at quantum dynamics and quantum mechanics. This is usually achieved by the eigenstate thermalization hypothesis, which I've written here. The eigenstate thermalization hypothesis is an ansatz on the matrix elements of our observable A in the energy eigenbasis. So in particular, I always lose. Okay, there I am. So in particular, the diagonal entries of our observable will be a smooth function of energy. And a big thing to note here, especially for this talk and what we're going to talk about, the off-diagonal elements are exponentially suppressed by the thermodynamic entropy S. Now, the rest of the equation isn't super important, so I won't talk about it, but basically, this ansatz is a generalization of random matrix theory. And random matrix theory is very important for the study of quantum chaos. So important properties of ETH is firstly, thermalization in ETH is actually an if and only if statement. So thermalization implies ETH, and ETH implies thermalization. So it's quite a strong statement. And next is that ETH implies ergodicity in the strong sense. And what I mean by that is you actually don't need any time averages to recover the equilibrium expectation values given to us by the ensembles of statistical mechanics. So a good way to see this is in the following way. If we were to look at this quantity sigma a squared, which is the infinite time average distance between our observable's expectation value in time and its equilibrium value, then what we would find is that if we assume ETH is true, then these fluctuations around equilibrium are upper bounded by something that is on the order of e to the negative of the thermodynamic entropy S. Now, the thermodynamic entropy is extensive, so it scales like the system size. So these fluctuations are exponentially suppressed in the system size. Now, what this tells us is that if you were to randomly select some time t, and then you were to compute your observable's expectation value, then interestingly, you are very unlikely to find that it is distinguishable from the equilibrium expectation value given that this formula, or given that the eigenstate thermalization hypothesis is true. So in this field, or in this line of research, there are three broad time regimes that one might be interested in. Firstly, does such an equilibrium exist? So this is sort of the start, the equilibration process. And if it does exist, how long does this equilibration process take? So given some information about the initial conditions, might I be able to predict how long the process might take? Second, can we describe equilibrium with the usual ensembles of statistical mechanics? Now, this is usually, as I've mentioned, explained using the eigenstate thermalization hypothesis. And three, once the system is in equilibrium, does it actually stay there? So is equilibrium actually stable? So there are several missing ingredients to understand all three of these. For example, for number two, we have no closed form sort of analytical proof that singles out any class of models for which the eigenstate thermalization hypothesis is satisfied. We do have ample amounts of numerical evidence, however. Now, for today, what we're going to do is we're going to focus on number one and number three here. So we're going to forget about the thermal average for today and just talk about the path to equilibrium, and then eventually we will talk about recurrences. So our focus today, equilibration and recurrences. So as I've said before, we are expecting that our observable will eventually relax to its equilibrium value. And so when you're studying something like this, sometimes you might want to write down the following function and study its properties. So we could study the finite time average, distance between the observable's expectation value and its equilibrium value. Now, in general, what we would expect is, in this scenario, that this function should go to 0 in finite time under reasonable assumptions. It's also quite common, so that you don't miss recurrences, to study just the distance itself and avoid the averaging, but the intuition is the same. So what's the state of the field? A very interesting bound that you can come up with is the following. If you do let tau go to infinity, then sigma a squared can be bounded above with the following formula, where, let me find where this guy is again. So we have the largest singular value of a to the power of 2 times the purity of the diagonal ensemble. Now, this might not intuitively sort of immediately tell you that these fluctuations are very small. But in fact, the purity of the diagonal ensemble decays exponentially fast with respect to system size. So this is an infinite time statement, a very powerful one. But one might want to be able to make finite time statements. But finite time statements turn out to be exceptionally difficult to make and to prove. And the reason for this is that we've basically sort of tasked ourselves with solving a very complex dephasing problem. So if we take our observable's expectation value in time, subtract off the equilibrium point, which makes our new equilibrium point 0, what we're left with is a huge sum of complex numbers v subscript alpha, all rotating around in the complex plane with frequencies g subscript alpha. From a numerical perspective, this is a very difficult thing to investigate because there is an extraordinarily large amount of terms in this sum for even modest system sizes. And analytically, it is very difficult to have sort of any analytical control over the terms in this sum without introducing some non-physical assumption. So just for your viewing pleasure, here is an example of this dephasing. What we see here is that at t is equal to 0, we have a very atypical configuration of our complex numbers, all sitting on the on the real axis. And as I click play, immediately we start to see, a very complex but very dense swarm start forming around the equilibrium value. So a potential way to make progress then would be to study the following probability distribution function. So suppose I gave you some function of time, f of t, and so with that, the p of x is the probability that if we choose some random time t, the value of our function is exactly x. So the mean of our function is then the following expression, quite intuitively, and the moments of our distribution will be the following expression for kappa q. And basically the interesting thing about our results is that if you can prove, given your dynamical function f of t, that the moments are upper bounded by q times g to the power of q, then all of the preceding results that I will show you will hold. G is going to be expected to be some small quantity that will be system size dependent, and it should go to 0 with respect to system size. So again, looking at this probability distribution function, we have our moments. Now it's important to note that usually this is not the most optimal bound, it's just a convenient bound to get to the next statement. And that is that we can prove the following conditional probability statement, which is that the probability of finding your dynamical function f of t delta away from its equilibrium value is exponentially suppressed with respect to delta. And we also have a division by g in the exponential, so basically what this means is that if g is a very small number, this bound will be extremely tight. We expect f of t to highly concentrate around its equilibrium value. So what types of models are we interested in? Well, if you look at our article, we don't just consider this class of models, but for what I'll show you today, the model that we're interested in, or the class of models that we'll be interested in, are models with so-called generic spectrum. And so what we're going to require is that our model has a non-degenerate spectrum, and we are going to require that the sums of the eigenvalues, or the sums of two eigenvalues, are also not degenerate. And we will require this for higher order sums of the eigenvalues as well. So this is definitely a strong assumption. So a possible mathematical justification is the following. The probability of uniformly choosing a non-generic Hamiltonian is 0. Now a more physical justification would be that in the literature it's expected that quantum chaotic models will have this property. So then choosing f of t, our dynamical function, to be our observable's expectation value in time, what we can do is we can prove that the moments are upper bounded in the following way. So we have q times the largest singular value of a times the square root of the purity of the diagonal ensemble, So as I've pointed out, this is the small number g, and so we do know that this will go exponentially fast to 0. So then we get the following concentration bound for how tightly the observable a of t will sort of concentrate around its equilibrium value a of infinity, where we have the purity of the diagonal ensemble in the denominator here in the exponential, which again, so basically what this will give us is that the probability will be doubly exponentially suppressed with respect to system size. So now let's move on to recurrences. Let's use these results for recurrences. So just to remind you of the Poincare recurrence theorem, the Poincare recurrence theorem tells us that any closed quantum evolution eventually returns arbitrarily close to its initial state in finite time. So an important question to ask ourselves is, does this conflict with our story of equilibration and the emergence of statistical mechanics? And the resolution to this problem is that recurrences should occur at extremely long times. So we shouldn't have to actually worry about the recurrences, assuming our system size is sufficiently large. And so just some jargon, basically I'm going to call my recurrences, or I'm going to label my recurrences with 3 labels. Firstly, U. So U that you see down in equation 32, U will be how close we get to our initial value. And then delta is going to be how long the interval is that our recurrence takes place. Okay, so that's all it means. It's nothing super fancy. And so to investigate this, we're going to investigate the average spacing of the recurrences. So defining the nth recurrence, we define it such that it is always less than, or it's always previous in time to the n+1th recurrence. And then we will define the average spacing of the recurrences with the following limit function. Now, it's not immediately obvious why this is an interesting way to go about this investigation, but let me give you an example. So again, let this black arrow be the arrow of time, and let's say these red dots label these dots label specific recurrences. So in our example, we will assume that our dynamics have an almost period that contain 3 recurrences, right? So then if we look at our sequence of the nth recurrence divided by the number of recurrences, n, and we only evaluate our recurrence at the almost period, what you should see, or what you might be able to convince yourself of, is that this sequence will look like 1 over the density of the recurrences. So if this number gets very big, if big T gets very big, then what that means is the recurrences are extraordinarily sparse in time. So if we then just look at our recurrences and we say that, the total distance, I always lose where this is, the total distance is CA away from, our starting position to our ending position, then we can come up with this generic bound for the average spacing of the recurrences here, which we see a doubly exponentially large scaling. So to put this on more sort of intuitive grounds, basically we expect the recurrences to be pushed away as e to the n, so it's doubly exponentially pushed away in time as we increase the system size. So as you can see here, we have t, the average recurrence time, would be greater than some constant that's related to the equilibration timescale, or it is the equilibration timescale, times e to the power of something at least on the order of 1 over the square root of the purity of the diagonal ensemble, which, as I've said, goes to 0 exponentially fast in the system size. So that's the end of the talk. Basically what we did was we derived a very tight concentration bound for equilibration in generic non-integral models. So similar results also hold for the fidelity, and weaker bounds can be found for free models. We use these bounds to provide then lower bounds on the quantum recurrence time. So this recurrence time diverges to infinity as we add degrees of freedom to the lattice. It diverges to infinity doubly exponentially fast. Now that's it for this video. Let me know if you have any questions in the comments, or you can ask them in the Discord channel, which is sort of picking up speed in terms of discussions on many body physics and things like quantum field theory these days. So thank you for watching if you've made it all the way to the end. If you did, feel free to like, subscribe, and leave a comment below.